Hi, and this is Vini. I'm going to talk about ECOS in the tiny house. Um, the ECOS is the Embedded Configurable Operating System. It is an open source, royalty-free real-time operating system. Um, it is intended for embedded application. The system is targeted at high performance, small embedded system. For such system, an embedded form of Linux and other commercial OS would not provide the streamlined software required. This is the ECOS configuration tool. Seen by the tool user. Each of the items on the list in the left hand window can be selected or deselected in order to configure the ECOS configuration tool. In the ECOS configuration tool, it consisting of a specific list of items in order to configure the ECOS. It consisting of synchronization, message blocking, and a priority inversion, enabling the priority inheritance. It also consisting of the properties of the threads, where it can priority inversion. It has a list of the properties of the process which can be configured in the ECOS. This is the loading and ECOS configuration. It shows a typical example of overall process of creating the binary used to execute in the embedded system. This process is run in the source system like Windows or Linux platform, and executable image is designed to execute a targeted embedded system such as a sensor in an industrial environment at the highest software level application source code for a particular embedded application. This code is independent of the ECOS but makes use of the application programming interface to sit on the top of the ECOS software. There may be only one version of the application source code, or there may be variations of different versions of targeted embedded platform. In this example, GNU makes a GNU make utility is based to selectively determine which piece of the program need to be compiled or recompiled. It sees the application source code, and if it finds any GLE errors, it has to be recompiled. Then application source code is passed to the GNU cross compiler, and this is passed to the linker where it attached some of the libraries in the targeted architect library, and then produces the executable file. The program needs to be compiled and recompiled based on the modified version of the source code, and issues the commands to recompile them. In this GNU make utility, when the source code application source code enter and the GNU cross compiler is compiled, so if there is a modified version in the source code, it receives a command to recompile them. Then after recompiling them, it passes the GNU compiler, which includes the libraries and target architecture library. Then it produces an executable file. This is the ECOS layout structure. The key design requirement for the ECOS portability to different architecture and platform with a minimal effort. To meet this requirement, ECOS consisting of layered architecture. This ECOS layered architecture consisting of hardware abstraction layer, kernel, input-output device drivers, standard C library, user application code. The layer in the UCAS, the lower layer in the UCAS is hardware abstraction layer. It presents the consistent API with upper level, provides the API which is required for upper layer, and it is different for each hardware platform. For each hardware, the hardware abstraction layer is different. There is no hardware abstraction layer for, hardware abstraction layer is different for each hardware. This shows the hardware abstraction layer of ARM and PowerPC architecture. In this PowerPC architecture, this enables the hardware. This code tells the hardware abstraction layer how it enables the interrupts in the ARM architecture, and in the PowerPC architecture, it is with respect to enabling the interrupts in the architecture using the macros. Hardware abstraction layer modules are architecture. It has a processor family type, variant. It supports a feature specific processor. Platform supports the type 2 separate product. In case of architecture, it defines a processor family type. This module contains some code necessary for the processor startup, interrupt delivery, context switching, and other functionality specific to the instruction set architecture of the processor family. The variant, it supports the feature of the specific processor in the family. An example of a supported feature is an ANSYS module such as a memory management unit. In the platform, extended the hardware abstraction layer supports two tightly coupled peripherals like interrupt, controller, and timer devices. This module defines the platform as board that includes the selected processor architecture and variant. It includes the code for startup, chip selection configuration, interrupt controller, and timer devices. Next layer is UCAS kernel. It has a core objective, low interrupt latency, low task switching latency, small memory footprint, deterministic behavior. In case of the low memory latency is the amount of time taken to respond to an interrupt and begin the execution of interrupt subroutine. Low task switching latency is it is the time taken from when a thread becomes available to when actual execution begins. In small memory footprint, it is the memory resources for the code, program, and data are kept to minimum by allowing all the components to configure memory as needed. In the deterministic behavior, throughout all aspects of the execution, the kernel performance must be predictable and bounded to meet the real-time application requirement. The core functionality needed for developing a multi-threaded application is an ability to create a new thread in the system either during the startup or when the system is already running. A control over the various threads in the system. A choice of scheduler determining which thread should currently be running. A range of synchronization filters allowing the threads to interact and share the data safely. Integration with the system supports for interrupt and exception. Some of the functionalities is typically included in the kernel of an OS is not included in the OS kernel. For example, memory allocation, device driver. This makes us learn the complete kernel. Example, memory allocation is handled by a separate package. It is not included in the ECOS kernel. Similarly, each device driver is a separate package which is in turn not defined in the ECOS inside the ECOS kernel. Input-output system. ECOS input-output system is a framework for supporting the device drivers. A derivative of input-output system is a framework for supporting device driver. A derivative of driver for used variety of platforms providing the ECOS configuration kit. These include the drivers for serial devices, Ethernet, flash memory interface, various input-output interconnects such as a peripheral component interconnect and universal serial bus. In addition, user can create and develop his own device drivers. The principal objective of the input-output system is efficiency with no unnecessary software layering or extraneous functionality. Device drivers provide the necessary functions for input-output, buffering, and device controller. Device drivers and other higher layer software may be implemented directly in the hardware abstraction layer, which is appropriate for specialized kernel type functions if needed, and the device driver is implemented using the kernel APIs. The three levels in the interrupt model are interrupt service routine, default service routine, and the threads. Standard C library. There is a complete standard C runtime libraries provided in the ecosystem. ECOS scheduler has bitmap scheduler, multi-level scheduler. The bitmap scheduler provides a efficient scheduling for a system with a small number of threads that may be active at any point in time. In the multi-queue scheduler is appropriate when if the number of threads are dynamic, or it is desirable to have multiple threads at the same priority level. The multi-level scheduler is also needed if a time slicing is desired. If the time slicing is desired, bitmap scheduler supports a multiple priority levels, but only one thread can exist at each priority level at any given time. Scheduling decisions are quite and the scheduling decisions are quite simple. With this scheduler, when a blocked thread becomes ready to run, it may preempt the thread of a lower priority as shown, and a thread can be suspended because it is blocked on a synchronization primitive, because it is interrupted, or because it relinquishes the control. And because there is only one thread at most at each priority level, the scheduler does not make a decision to which thread at a given priority level should be dispatched. The bitmap scheduler is configured as 18, 8, 16, 32 priority level. A simple bitmap is kept at the threads that are ready to execute. The scheduler will only determine the position of the most significant one bit in the bitmap to make a scheduling decision. Next can show is multiple queue scheduler. In this, it supports 32 priority levels. The multiple queue scheduler allows for multiple active threads at each priority level, limited only by system resources. This figure shows the nature of the multi-level queue scheduler. A data structure represents the number of ready threads at each number of ready threads at each priority level. When a block thread becomes ready to run, it may preempt the thread to a lower priority. ECOS thread synchronization has four classic mechanisms. That is, ECOS thread synchronization has a classic mechanism includes mutex, semaphores, and condition variable. This classic synchronization mechanism is mutex, semaphores, condition variable. In addition, ECOS supports a two synchronization communication mechanism that are common in a real-time system, namely event flags and mailboxes. Finally, ECOS kernel support spin locks, which are useful in the symmetric multiprocessing system. In this ECOS thread mechanism, we talk about the mutex now. Mutex is used to enforce mutually exclusive access to a resource, allowing only one thread at a time to gain the access. There are two types of mutex that are locked and unlocked. Next synchronization mechanism is semaphores. This semaphores it supports a counting semaphore. It is an integral value used for signaling among the threads. Some of the examples are sync semaphore pose. It increments a semaphore count, and sig semaphore wait. It checks the value of semaphore count. Next synchronization mechanism is condition variables. And this, it is used to block a thread until a particular condition is true. It is used with mutex to allow the multiple threads to access the shared data. Some of the examples of the condition variables are sig condition wait, sig condition signal, sig condition broadcast. Until this condition is verified to be true, it blocks the current holding thread. This is the example of the mutex. It enforces a mutually exclusive access to resources, allowing only one thread to gain access at a time. Mutex has two states as set, locked and unlocked. Similarly, binary semaphores, when a mutex is locked for one thread and any other thread attempt to lock the mutex is blocked. When a mutex is unlocked, for only one thread blocked and the mutex unblocked and allowed to lock the mutex to gain the access to the resources. The mutex differs from the binary semaphores in the two aspects. The thread that locks the mutex must be one to unlock it, but it is possible for one thread to lock a binary semaphore and for another to unlock it. The other difference is that mutex provides a protection against the priority inversion, whereas the semaphore does not. ECOS kernel can be configured to support either the priority inheritance protocol or priority ceiling protocol. As this example shows, there is a mutex that is allocated. The mutex is set for the resources, and for the resources after use, the mutex has been released. A condition variable is used to block a thread until a particular condition is true. The condition variables are used with the mutex to allow multiple threads to access the shared data. In ACOS, condition variables are typically used in conjunction with the mutex to implement long-term wait for some conditions to become true. As this example shows, there is a resources allocated, and it checks whether if the resource count is equals to 0, then the condition variable condition variable will set, and only after this resource is wait, and it will decrement the resources, and it when the resources is leaving, it put back the resource pool and decrements the resources count, and this after this condition evaluates to true, it unlocks the resources. First it locks the mutex, and after it locking the mutex, it checks for the condition and wait for the resources, and if the resources is free, it allocates the resources, and after allocating the resources, the condition evaluates to true and allocates the resources, then it finally unlock the resources. Here this example shows the continuation, that is it locks the mutex and frees the resources, and the condition is set to wake up any waiting and allocate, and then unlocks the mutex. Next to talk about is TinyOS. TinyOS takes the process of streamlining too much further down, resulting in a very minimal OS for embedded system. The core of OS requires only 400 bytes of code, and the data memory is combined. TinyOS represents a significant departure from the other embedded operating system. This TinyOS is not a real-time OS. The reason for this is it is expected to workload which is in the syntax of wireless sensor network. Because of the power consumption, the devices are off most of the time. Devices are it is puts off most of the time. Applications tend to be simpler with the processor contention not much of an issue. In the TinyOS, there is no kernel, as there is no memory protection, and it is component based OS. There are no process. And the OS itself does not have a memory allocation system. Interrupt and exception handling is depend upon the peripheral, and it is completely non-blocking, so there are few explicit synchronization primitive exists in the TinyOS. Next comes here is the goals of the TinyOS. With the tiny distributed sensor application in mind, the following are the goals were set for the TinyOS. That is high concurrency, operate with a limited resource, adapt to the hardware evolution, support a wide range of applications, support a diverse set of applications, be robust. In the high concurrency, it is in a typical wireless sensor and network application. The devices are concurrency intensive. Several different flows of data must be kept moving simultaneously. While sensor data is input in a steady stream, the process result must be transmitted in the steady stream. Also, external controls from the remote sensor or base relation must be managed. In the operate with a limited resources, a target platform has limited memory and the computational resources and run on the batteries or a solar power. A single platform may offer only a kilobytes of a program memory and hundreds of bytes of the RAM. The software must make efficient use of the available process and the memory resources while limiting the power consumption. The adapt to hardware evolution, hardware is instant evolution. An application and most of the system services must be portable across the hardware generation. It should be possible to upgrade the hardware with a little or no software change if the functionality is the same. With respect to support and language of application, an application exhibits a wide range of requirements in terms of lifetime, communication, sensing, and so on. A modular general purpose embedded operating system is designed so that standard approach leads to economies of scale in developing applications and support software. Supporting a diverse set of platforms and tools as general purpose embedded OS is desirable. In the B router, once deployed, a sensor network must be run unattended for months or years. Ideally, there should be a redundancy both within a single system and across the network sensor. However, both types of redundancy requires additional resources. Once the software is characteristic that can improve the robustness is to use highly modular standardized software components. The TinyOS components it is an embedded software system built using the TinyOS consisting of a set of modules called components, each of which performs a single task or a set of tasks which is interfaced with each other and with the hardware in the limited and well-defined ways, such as single hop networking, ad hoc routing, power management, times, or non-volatile storage control. All components of the TinyOS configuration have the same structure as shown. The shaded box in the diagram indicates the component which is treated as an object that can only be accessed by the defined interface, indicating white boxes. The component indicating white boxes, the component may be hardware or software. And next shows the timer and configuration. A component are organized into configuration by wiring them together at their interfaces and equating the interfaces of the configuration with some of the interfaces of the component. The simplest example is next comes here is TinyOS scheduler. It operates across all components. Virtually all embedded system using TinyOS will be uniprocessor system, so that only one task among all the tasks in the components may be executed at a time. In the scheduler is a separate component. It is one of the portions of the TinyOS must be present in any system. The default scheduler in the TinyOS is a symbol of FIFO. The task is posted to scheduler, placed in the queue either as a result of an event which triggers the posting or as the result of specific requested by a running task to schedule another task. The scheduler is power aware. It means that scheduler puts the processor to sleep when there is no task in the queue. The peripheral remains operating so that one of them can wake up a system by means of hardware events signal to a lowest level component. Once the queue is empty, another task can be scheduled only as a result of direct hardware event. This behavior enables the efficient battery use. This below shows the configuration assembled from the software and the hardware components. This is a simplified example called surge operation. Performs a periodic sensor sampling and uses a ad hoc multi-hop routing over the wireless network to deliver the sample to the base station. This comes here is TinyOS resources interface. It has a powerful set of conventions for dealing with the resources. consisting of it has dedicated virtualized functure. In the dedicated a resource that a subsystem needs exclusive access to at all times. In this class of the resource, no sharing policy is needed, since only a single component ever requires use of said resources. The example of this dedicated MS abstraction included interrupts and counters. In the virtualized, every client of virtualized resources interacts with it as if it were dedicated resources, with all virtualized instances being multiplied on top of the similar underlying hardware resources. The virtualized abstraction may be used when underlying resources need not to be protected by the mutual exclusion. An example for this is graph or timer. Shared resource abstraction provides access to the dedicated resources through arbitrary component. The arbiter enforces a mutual exclusion, allowing only one user per client at a time to have access to the resources and enabling the client lock. This figure shows a simplified view of the shared resources configuration used to provide access to the underlying resources. It associated with each resources to be shared in an arbitrary component. This arbiter enforces a policy that enables the client to log the resource and then release the resources. This figure shows whenever the client requires the resources, they can log it, and after the process is completed, the resources can be released. Thus, I have explained the concepts of ECAS in the TinyOS. This completes my seminar. Thank you.